telephones, seismographs, cables, and certain data acquisition systems. We also have partnered with Seismic Source to supply seismographs, and we promote ParkSEIS MASW software. And it gives me great pleasure to introduce Dr. Choon Park, who will be handling this presentation. We have muted everybody because we don't really want the presentation to be interrupted. So if you have questions, I would request you to please use the raise hand and put your question in the chat box so that in the last 30 minutes, Dr. Park can answer your questions as they are raised, and Ajay will monitor them, and we'll try and answer all your questions. So without any further ado, I'll pass you on to Dr. Park. Thank you. Ajay, you can unmute Dr. Park.
Dr. Choon, can you yeah.
Can you hear me? Can you hear me now?
Yes, we can hear you, sir. Please go ahead.
Okay. So yeah, let me share my screen. Where should I go to share my screen?
There is an option in the left side to the 3 dots in between. There you can share.
Okay, Teams.
Where it says more.
Yeah. Open to share try. Can you see that, Choon?
Okay, more actions. Gallery.
Not more actions, it's just beside more action. There is an up arrow, you can see that.
Share desktop, there you go. Screen share. Do you see my screen now?
Yes, we can see your screen.
Okay, good. All right. Well, again, thank you very much, Anil, for the introduction. And I'm really glad to have this opportunity to reach out to you guys. And we are really glad to start this collaboration with the HGS India. And well, by the way, good morning here in America, and good afternoon in Europe, and I guess good evening in Asia. So I will briefly talk about the background theory and the procedures and the application of MASW for the first about 30 minutes. And then I will demonstrate the ParkSEIS software package that Anil was talking about. And the ParkSEIS software is the software package that we in the Seismic company sell as the MASW data analysis software all over the world. So I hope it'll be a good chance for all of you guys to see a first-hand experience of using a ParkSEIS software package during the last about 20 minutes. So what is MASW? Well, so let me talk briefly about the background, the theory, general procedure, and the common applications. There are many applications being made worldwide these days, but I will introduce a few or several typical applications. So it consists of these very simple 3 steps. So you collect so-called multi-channel seismic data in the field. by using so-called multi-channel data acquisition approach. And then that obtain the field data, field file, goes through 2 steps of data analysis. The first step is called the dispersion, and second step is called the inversion. And at the end, you generate this kind of 1D shear wave velocity profile. And this is the 1D shear wave velocity profile. As you can see here, horizontal axis is shear wave velocity, and it increases in this way. And the vertical axis is depth. So this basically presents shear wave velocity variation with depth. So again, MASW survey provides this 1D shear wave velocity profile at one location from the file that you collect by using multi-channel approach, multi-channel acquisition approach. Hello?
Yes, we can hear you.
Can you hear me? I had my screen froze for a couple of seconds. So if you repeat that measurements and analysis to generate the 1D profiles at successively different locations along a linear survey line, then you will come up with multiple number of 1D shear wave velocity profiles. And then you can use all of them to create this kind of 2D shear wave velocity cross-section. So you are looking at 2D shear wave velocity cross-section here. Horizontal axis represents the surface location, and the vertical axis is the depth. And the different colors represent different shear wave velocities. So for example, here, this the yellowish and the red colors represent the bedrock, which is about 700 or almost 1,000 meters per second. And this greenish and bluish colors represent 100 or 200 meters per second, which corresponds to usually overburden or soil. So why are we dealing with the shear wave velocity? Well, I guess all of us participating in this meeting this morning are dealing with the geotechnical engineering projects. So when it comes to geotechnical engineering, we deal with stiffness of ground materials. So what is a stiffness? It is a resistance to deformation. And there are 3 types of resistance, which are commonly represented by 3 moduli. One is called the Young's modulus, which is a material's resistance along to the deformation along the longitudinal direction. And the other one is called the shear modulus, which is a material's resistance to shear direction or mostly transverse direction. And the last modulus is called the bulk modulus. It is a material's resistance to volume change. So when it comes to geotechnical engineering, we can usually ignore this volume change, and we usually focus into these 2 moduli, Young's and shear moduli. So let's take a look at the defining equations for each modulus. Young's modulus defining equation is here, and the shear modulus defining equation is here, and the Young's modulus defining equation here. So if we look at those 2 equations, so we find that there are 3 parameters. First is the shear wave velocity. Second one is the density. And the last one is the Poisson's ratio or P wave velocity. They are linked together. So in theory, if we can measure shear wave velocity and density and Poisson's ratio independently and separately, then we will be able to come up with a very good evaluation of these 2 moduli of a shear modulus and the Young's modulus. But in reality, it is impossible. At most, we can expect to measure only one of them. If that's the case, then it has to be shear wave velocity because of 2 reasons. First, as you can see here, shear wave velocity is included as a square term in both equations, which means shear wave velocity is the most sensitive term. And second, for the other two parameters of density and Poisson's ratio, usually we have a very good approximation values. For example, when it comes to geotechnical materials of soil materials or soil particles, we know density is somewhere between 2.0 and 2.5 gram per cubic centimeters. So we can use 2.3 as a very good approximation value. And also for the Poisson's ratio, most of the soil materials, Poisson's ratio is somewhere between 0.4 and 0.49. So if we use 0.45, it can be a very good approximation value. Whereas this shear wave velocity can vary a lot. For example, a very soft soil shear wave velocity can be as low as 50 meters per second, whereas very competent bedrock shear wave velocity can be as high as 3,000 meters per second. So in shear wave velocity, there is a huge range. So that's why it has to be this shear wave velocity if we want to estimate stiffness of geotechnical materials. So I just explained about the importance of measuring shear wave velocity. And then here is the approximate shear wave velocity ranges for typical near-surface materials. For example, organic layer or topsoil may have a shear wave velocity somewhere between 50 meters per second and 100 meters per second. So whenever soil has a shear wave velocity lower than 100 meters per second, then we can say it is an extremely soft soil. And more 100 meters per second and 300 meters per second. So when shear wave velocity of soil exceeds 200 meters per second, we can call it stiff soil. And when the shear wave velocity exceeds 300 meters and lower than about 500 meters per second, then it is a kind of transition zone. It is a mixture of soil and bedrock fragments. And once the shear wave velocity exceeds 500 meters per second, then we can consider that as a bedrock. Again, this is approximate shear wave velocity range. So now, why are we then dealing with the surface waves? Well, remember this MASW stands for multi-channel analysis of surface waves, not shear waves. So, well, before that, take a look at the general types of seismic. There is a P wave and S wave. So usually, I mean, traditionally, people have been measuring these S waves to come up with the S wave velocities. And now we are dealing with this surface wave. And under surface wave, there are two types. One is called the Rayleigh waves, and the other one is called Love wave. Rayleigh waves usually have mainly a vertical component of vibration. Love waves usually have a horizontal component of vibration. And the MASW mostly deal with this type of Rayleigh waves, vertical vibration of seismic waves. So MASW is dealing with the surface waves, not shear waves. Why? Well, here we are looking at one of the very typical field files obtained by using 24-channel seismograph. And here we see very strong amplitude wave arrivals. They are surface waves. When we transform this into spectral energy, we see most of the energy here is in the form of surface waves. And the body waves, which are displayed here, and here, this is the first arrivals, which is usually refraction, and this is a reflection. Body wave energy takes less than 20% of total seismic energy generated. This wave that take more than 2/3 of total seismic energy generated. In other words, the surface waves are always strong. So when we use the surface waves, then we always have a very high signal to noise ratio. In other words, the data acquisition is a very, very simple and very easy, and you will always be able to come up with a very high signal to noise ratio. Now, why are we using then surface waves to come up with the shear wave velocities? Well, here is the diagram that shows the theoretical relationship between shear wave velocities and surface wave velocity. Surface wave velocity is determined by 3 parameters. One is the shear wave velocity, which contributes more than 95%. The other one is a P wave velocity or Poisson's ratio that contributes about 3%. The last parameter is density that contributes about 2%. So in theory, if we measure surface waves and analyze them to come up with the surface wave phase velocity, then we can come up with the shear wave velocity within the accuracy of about 95%. No, actually the accuracy is higher than that, because as I said earlier, we know pretty good approximation values for P waves or Poisson's ratio and density. So when we use those good approximation values, the final accuracy of evaluating shear wave velocity from evaluation of the surface wave velocity becomes almost 99%. So, but traditionally, seismic wave application for geotechnical engineering purposes have been usually focused into P wave velocities. Why? Traditionally, there have not been reliable seismic techniques to evaluate shear wave velocities within satisfiable accuracy range. Whereas P wave velocity, those there have been many techniques that can measure P wave velocity within a good accuracy. So, for example, this is a repeatability chart prepared by the Caterpillar company. I believe this chart was available almost 30 years ago. And as you can see here, this chart is based upon different P wave velocities around the materials. Again, at that time, there was no seismic technique available that can provide the shear wave velocities in a reliable manner. That's why this chart was prepared based upon P wave velocities. And I believe this chart will be soon replaced by shear wave velocities. And I know there are several institutes around the world where they are working on this topic. So let me talk about the schematic of general field survey deployment here. So the most important component is this multi-channel seismograph, and you have to have this seismic cable with a certain takeoff spacing. And then if it is a 24-channel seismograph, then this seismic cable will have 24 takeouts. Each takeout will have its own geophone connected, and you use this kind of sledgehammer to generate surface waves. And on the handle of that sledgehammer, you attach this hammer switch. So when you make impact, that hammer switch detects that impact and sends signal to this seismograph to start recording. So at that time, it becomes 0 time. And then the seismograph digitizes all the incoming analog signal from all these 24 geophones, and then sends those digitized data into this external laptop computer, where those data are saved as one file, which is called one field file, or sometimes called the one multi-channel record. So let me briefly talk about the background, the theory. How does it work? Well, again, this is surface wave method, and the most important property being utilized in this surface wave method is each wavelength dependent penetration depth. As illustrated here, you can see very short wavelengths of surface waves penetrate shallow, whereas the long wavelengths of surface waves penetrate deeper. So when there is no velocity change with depth, then both short wavelengths and long wavelengths will travel at the same speed. But if there is a velocity variation with depth, or if velocity increases with depth, then these long wavelengths will travel faster than these short wavelengths, because these long wavelengths, the seismic velocities are determined by this more larger area properties of the subsurface materials. So these short wavelengths are recorded in our data as high frequencies, and these long wavelengths are recorded in our data as low frequencies. So when we plot those phase velocities against the frequency, this is a dispersion curve chart. So horizontal axis is the frequency, and vertical axis is phase velocity. So when we plot those different frequency components of phase velocities, and when all those frequency components have the same phase velocity, then we will end up with this kind of horizontal line. Whereas if those different frequency components have a different phase velocities, then it becomes this kind of curve. So this curve is called the dispersion curve. And you can see here, depending on different shear wave velocity structure, the dispersion curve shape changes. So what we are doing here is we first measure this dispersion curve from our seismic data that we collect in the field. And then we try to back calculate the responsible shear wave velocity. For example, this dispersion curve is generated from this velocity model. And this number 3 dispersion curve is generated from this velocity. So this is a forward modeling, but we are actually trying to do inverse. We measure these dispersion curves first, and then try to back calculate the responsible shear wave velocity profile. So this is the background theory, and let me start talking about the applications. As I said earlier, there are so many applications nowadays being made all over the world. But I'd like to present here a few of typical ones. And this one is the wind turbine site characterization. Each wind turbine site in this project, which was executed while I was at the Kansas Geological Survey, which was 20 years ago. This is a Blue Canyon windmill farm in Lawton, Oklahoma. Each windmill tower site, planned tower site, was investigated by using MASW. So for each site, we provided a shear wave 1D shear wave velocity profile. So this is a 1D application of MASW, and those shear wave velocity profiles present the shear wave velocity variation for top 5 meter, or sometimes 10 meter, and sometimes 20 meters of depth. So this application is very similar to more popular type of application, which is often called the seismic site characterization, or VS 30-meter evaluation. And this is also 1D shear wave velocity application with the MASW, quite common nowadays. What it does is each site is classified into 6 different classes based upon average shear wave velocities for top 30 meters. Why top 30 meters? Well, the meaning of these different classes is that, for example, the class A, which has the highest average shear wave velocity, that site will go through the least amount of ground amplification under the same magnitude of earthquake. Whereas the last class, which has the lowest average shear wave velocity, that will go through the biggest ground amplification under the same magnitude of earthquake, which means this class is more dangerous than this class. Okay, so why is that the top 30-meter depth so important? I don't know exactly, but as I talked to those earthquake seismologists, they believe everything within that top 30 meters will determine the amplification of the ground when earthquake occurs. So that's why that this top 30 meter is very important, and also the shear wave velocity is a direct indicator of how much amplification each specific site will go through under a given magnitude of earthquake. So these are actual examples from different sites for 5 different classes, seismic site classes. And again, this is the 1D profiles. Horizontal axis is shear wave velocity, and vertical axis is depth. So this is an A class, which means shear wave velocity is very high, all the way down to about 30-meter depth. And this is E class, as you can see here, shear wave velocity is very low, all the way down to almost 20-meter. And now this is a 2D application of MASW surveys. Here we are looking at the 2D shear wave velocity cross-section. Horizontal axis is a surface distance, and the vertical axis is depth. And the different colors represent the different shear wave velocities. And the white and the blue colors correspond to very low shear wave velocities. White color is almost 100 meters per second, and blue color is about 200 meters per second. So these areas are overburden or very soft soil, and reddish color and yellow color represent the high velocities like 700 and 800 or 900 meters per second. So this part represents a very competent bedrock, red color zone, and then this part represent kind of weathered bedrock zone. So this type of 2D application is the most common type of MASW application nowadays. And this one shows the grouting soil improvement. In other words, they use the MASW technique to evaluate how much a specific soil improvement technique was. In this case, they use their own specific technique of grouting. And before they apply that grouting into a specific site of soil, they ran one MASW survey, which is this one. And after their grouting, they ran another MASW survey. So they came up with this cross-section after post-grouting, and they came up with this cross-section for the post-grouting. And then they subtracted this before grouting cross-section from this one, and then they came up with this cross-section. So this cross-section shows how much shear wave velocity improvement occurred at what depths and at what places along the lateral direction. So this is a very, very useful information. In other words, we can see here, shear wave velocity improvement occurred exactly at the depth range where they targeted by applying the grouting technique. And they can also know how much improvement they achieved from the grouting. And this shear wave velocity improvement is converted into shear modulus and also Young's modulus. So this is another popular application to the compaction evaluation. This is a specific compaction application used at the Minnesota Department of Transportation almost 15 years ago. They used this kind of a quadruple land streamers, and they were dealing with a very shallow depth range, like at the top 1 meter depth range. And So each of these panel represent plan view map. In other words, the horizontal axis is a surface distance, but the vertical axis represents not depth. It represents the transverse direction. So this one panel represents the shear wave velocity variation along both the longitudinal and transverse direction for top 30 centimeter depths. And this panel represents shear wave velocity variation for top 1 meter depth range. And they come up with the results at 5 different stages of that road construction. And we can see the shear wave velocities are gradually increasing during the first 3 stages, and then it increases. I mean, they increase very rapidly for the last 2 construction or compaction stages. So let me briefly talk about the field operation and equipment, and this is a classic photo that illustrates garbage in and garbage out to emphasize the importance of collecting very good field data. Well, with the MASW, as I said earlier, you can always achieve a very high signal to noise ratio. So you don't have to worry about the failure of your data acquisition. In fact, with the traditional body wave surveys, it is very difficult to collect data with a very good signal to noise ratio. But with the MASW, it is more difficult to collect bad data than to collect good data. So if you can make a small mistakes here and there, you will still be able to come up with a very good data with a high signal to noise ratio. Again, this is a typical schematic of the field deployment. This is a seismic cable with a specific takeoff spacing. So this takeoff spacing is fixed for the given seismic cable. So whenever you order your seismic cable, you have to specify this spacing. So for most of the MASW applications, we recommend this spacing to be either 2 meters or 3 meters. Okay, so and then for each takeoff, you connect individual geophone, which is planted right beside each takeoff. So all this seismic cable is connected to this seismograph, and all analog signal will go into this seismograph and then digitized and go into this laptop computer and saved as one file. The most important part of your field geometry is your receiver array length. Your receiver array length has to be at least twice of your maximum investigation depth. For example, if your maximum investigation depth is about 10 meters, then your receiver array length has to be at least 20 meters long. So we usually take between twice and 3 times of Gmax. So if it is 20 meters that the receiver array has to be long, then you divide that 20 meters by the number of your channel. If you have a 24 channel, then there will be 23 divisions, right? So you divide the 20 meters by 23, then it will be about 0.9 something meters. Then you can use 1 meter. So you can round it up. So that's how you determine your receiver spacing. So again, this is the most important concept. Well, this concept is very analogous to radio wave antenna concept. But whenever you need to capture long wavelengths of radio waves, then you have to use a very long antenna. Whereas if you want to capture very short wavelengths of radio waves, then you have to use a very short antenna. So the same concept applies to seismic survey, especially for this MASW survey. So MASW surveys, this receiver array concept is analogous to antenna concept in radio wave transmission. So this is a roll-along acquisition for 2D cross-section generation. Whenever you need to generate 2D shear wave velocity cross section, you have to collect your data in this roll along mode. So this is the source receiver chart. So horizontal axis is distance, and the vertical axis is file number. For example, file number 1.dat saved during the data acquisition. The first channel, the last channel is located at x equals 0, and the receiver spacing was 1 meter. So the first channel here is located at x equals 23 meters. And the source shot offset, which is the distance between shot point and the closest receiver, it was 6 meters. So the first shot point was x equals 29 meters. And then everything moved by the same distance of 1 meter, okay? And then it repeated 24 times and collected a total of 24 field files. So your mode of data acquisition have to be very much consistent. So this is so-called roll-along mode of data acquisition. So if you use the conventional geophones with a spike, then once you collect one seismic file, then you have to move everything by certain distance. So at best, you have to move 1 or 2 geophones on the front side to the other end of the receiver array, and then you have to unplug all the geophones, and then you move your seismic cable certain distance, and then you plug all those geophones again. So it'll be very much time-consuming and labor-intensive. Instead, if you use this kind of land streamer, which is just a common belt on which you place all the geophones together. So once you collect data at one location, all you need to do is just pull this belt, then everything, all 24 geophones will move as one unit. In other words, this is very, very convenient. This land streamer approach will speed up your survey by more than probably 10 times. And the reason why you can use this kind of land streamer is, as illustrated here, you have to take out the spike at the bottom of geophone. The purpose of this spike is to ensure good coupling between geophone element and the ground. But with land streamer, you have to take it out, and then you place the geophone on top of this heavy metal plate. So this heavy metal plate provides a good coupling with the ground through the gravity of that matter. And this coupling may not be as good as the conventional spike coupling, but still it is good enough because, as I said earlier, surface waves are very strong. So I would recommend using this land streamer for 2D survey. And your seismic source is very important as well. And as I said earlier, this sledgehammer is the most common type of seismic source used for MASW surveys. People commonly use about 10 kilogram size sledgehammer for the most common depths of investigation, which is about 20 meter or sometimes 30 meter. And this X max, which is distance between shot point and the last geophone, this X max, which is basically determines the investigation depth. For the sledgehammer, you can go as far as 100 meters, and as you use more and more powerful source, then you increase that distance, which means you can increase your investigation depth. And if you use a dynamite, then your X max can become as far as 1,000 meters, which means you can achieve 500 meter investigation depth. And strike plate is also important with the MASW survey. Metal strike plate has been used conventionally for most of the traditional seismic surveys, which are body wave surveys, like the refraction and reflections, in which high frequencies are very, very important. But with the MASW survey, low frequencies are more important. So to generate more energy into the low frequencies, this kind of softer material strike plates are better, like a plastic or polyethylene strike plate, or sometimes a simple bulky wood plank may be able to generate better signal in terms of surface waves, because they will put more energy into the lower frequency side. And now this is the anatomy of geophone. As you can see here, it is basically spring and mass system. And each geophone has its own resonance frequency. For example, when you say this is a 4.5 Hertz geophone, then its response curve is like this. So horizontal axis here is the frequency, and the vertical axis is the response amplitude. So at 4.5 Hertz, you see the here, even with the 4.5 Hertz phone, you can record all the way down to almost 1 Hertz of surface waves, because the surface waves are very strong. So 4.5 Hertz vertical phones are the most common type of geophones used for MASW surveys. And now let me talk about the data analysis. As I said earlier, there are 2 steps. First step is called the dispersion, and second step is called the inversion. And well, before that, let me briefly talk about this source receiver setup. Whenever you purchase your seismograph, it comes with its own acquisition software, which is illustrated here. And within acquisition software, there is an option in which you can actually enter location of Shah point and all 24 geophones as illustrated here. So once you do that, then all those information is encoded into the header of the file saved. But usually people don't do that. I don't do that either, because it is very much tedious and very much time consuming. And once you are in the field and you participate in the field operation, there are so many things occurring at the same time. So it is so easy to make a mistake. So instead, people keep field note. So they bring this kind of printout, and then they put a few key information for each file. For example, the file saved as 1001.dat, I put shot location, like shot was x equal 0 meters, and then location of the first geophone, like x equal 8 meters, and then location of the last geophone, like x equal 31 meters. And then on this top portion of the field note, you put the receiver spacing. So as far as you keep that kind of information on this separate field note, then you don't have to go through this field geometry specification during your data acquisition. And then once you come back into your office, and when you start your data processing by using a separate software package like ParkSEIS, then at the beginning, you will go through this source receiver setup within that program. Okay, and then that part of the program will show the setup that you enter at the end of that process by using this kind of a two-dimensional chart, from which you can tell if all your parameters were correct or not. So and then after that, so this source receiver setup is considered as a pre-processing, and then the real data processing occurs for dispersion and inversion steps. And let's take a look at each step. So this is the dispersion step. So your raw data or field data is passed into this dispersion image generation as is. You don't apply any pre-processing like a filtering, escape filtering, bandpass filtering, gain control. You don't do anything. You just pass the raw data into this wave field transformation technique, which creates this kind of dispersion image. And then from that image, you extract this dispersion curve. So I will demonstrate this in a minute by using the ParkSEIS software. So once you extract this dispersion curve, then this is the most important part of your measurement data. And then you pass that measured dispersion curve into next step of analysis, which is inversion. At the beginning of that inversion, program will create so-called initial velocity model from this measured dispersion curve. There is a well-known empirical formula that can create this initial shear wave velocity model. So this is a shear wave velocity model. Horizontal axis is a shear wave velocity, and vertical axis is depth. So this shear wave velocity model is not very much accurate, but it is approximation. Okay, and then the program will generate a theoretical dispersion curve corresponding to this shear wave velocity model, and then compares that theoretical dispersion curve against measured dispersion curve. And of course, it will not match perfectly, but the program will go through where the biggest discrepancy exists, and then it will go back to this initial model, and it will know where or which layer of shear wave velocity has to be changed, how much. So it will update initial shear wave velocity model and create another theoretical dispersion curve and compares that new theoretical dispersion curve against your measured dispersion curve again. So it will repeat that process until you come up with the final shear wave velocity model whose dispersion curve, theoretical dispersion curve, matches your measured dispersion curve most closely within, let's say, a few % of error. So that's the inversion process. So with the MASW, we can come up with basically 3 key information. First information is bedrock depth, and the next information is the shear wave velocity of overburden, and the last information is the shear wave velocity of bedrock. So here are the relative confidence for all those 3 parameters. Bedrock depth evaluation is very, very high. So we can have a very high confidence in the bedrock depth evaluation. And then shear wave velocity evaluation of overburden is also very high. And then the shear wave velocity evaluation of bedrock is next. So the bedrock depth evaluation has about 85% of accuracy in general. Sometimes it can give you 95% or 99% of the accuracy. Sometimes the accuracy can be as low as the 70%, like that. But still, I believe that this much accuracy is very good in comparison to all other physical approaches available nowadays. So when it comes to MASW data analysis software package, it has to have all these common steps of source receiver setup, dispersion, inversion, analysis, and then proper way of output presentation. And although theories for dispersion and inversion are very much well known, and there have been so many publications under these 2 topics came out during last couple of decades. When it comes to software packaging, you know, the algorithm has to be updated continuously as the new techniques are published. And also there are many places that need empirical calibrations. And the graphical user interface, the importance of that cannot be overemphasized. So when it comes to this ParkSEIS software package, it is the first, oldest, the most advanced, the most user-friendly MASW data analysis software package. This is not what I say, this is what people say. I believe this slide is the only slide having the sales pitch of today's presentation. But anyway, this software package evolved from the research software package that I developed while I was working at the University of Kansas as a PhD student in early 1990s. So the early program was a DOS program. So it continued to evolve next year about 3 decades to become this ParkSEIS software package. So what I'm saying here is it is a very much reliable MASW data analysis software package, and it is also very much user-friendly, which you will see in a minute. So now let me start demonstrating ParkSEIS software. I will use 2 sets of field data. They are actual field data sets. First data I will use to come up with a 2D velocity cross-section. And this data set was collected at one of these housing construction area. And they collected many files, but I'm going to use only first 12 files to illustrate to demonstrate the software package. And this site has this kind of subsurface in comparison to this kind of subsurface. Here, you see very well-defined distinction between the bedrock and the overburden, but usually the soil and bedrock, in between those two, there is a kind of transition zone. So this site has that kind of transition zone as well. So let me start the demonstrating. And yes, they use the render streamer to collect these files. And the receiver spacing was 1 meter, and the source was located in front of the channel 1, and that shot distance was 8 meters. And collecting 1 file, everything moved by 2 meters, and they repeated many times. But I'm going to use the first 12 files today. So let me start using this ParkSEIS. So you go to process here, and then to the velocity cross-section from field data in seg2 format. By the way, the file that you save by using your Seismic has to be saved in seg2 format, which is engineering standard format. So I go to here, and here are the 12 files. So I'm importing all of them at the same time. And then the program detected that there is no field geometry encoded in the info file. So it recommends me to run source receiver setup. Okay, and the run wizard is the most often used option. So I click run wizard. Here, the most important part is I have to make sure the correct distance unit. Right now, it's clicked at the feet, because it is the unit it detected from the file header, data header of the info files, which is not correct. So they use the meter unit. So I override to the meter and go to next. And then here it asks what was the survey type. First button means it was active survey. Active survey means you use active source like a sledgehammer to generate surface waves. The second button is a passive survey, which is you don't use any active source, but you completely rely on ambient vibration, like the vibrations generated from traffic. And the last one is you use your active source to start recording, but your recording time is long enough to include ambient vibrations. In other words, a passive surface waves as well. So this is an active passive combined survey. So in this case, the data was collected by using active survey approach. So I have to select the first button. And then next one is the type of receiver array. Almost always people use 1D receiver array, and the 2D receiver arrays are sometimes used for passive MASW surveys. But in this case, it is a 1D array. So I select this one. And then what is the receiver spacing? This is the most important parameter. It was 1 meter. So I type it 1. And then where was the source location? The first button means source was located off the first channel. The second button means it was located in between first and the last channel. The last button means source was located off the last channel. It is this one. Source was located off the first channel. Okay. And now what was the distance? Shot distance here. It was 8 meters. Okay. And then this is a graphical summary of all those 3 critical information that I entered. So looks like everything is correct, and you move to next. And now, how did the source and receiver array move? The first button means both sharp point and receiver array moved together into either direction. The second button means receiver array did not move, but sharp point moved into either direction. The last button means sharp point did not move, only receiver array moved into either direction. In this case, it should be this one because they used land streamer. So each time they moved both sharp point and receiver array as one unit. Into which direction is to be specified on next page. So into which direction? This one means everything moved into receiver array, and this one means everything moved into sharp point. It was this one. Everything moved into receiver array. And how much distance? It was 2 meters. Every time they moved everything, both land streamer and sharp point, by 2 meters. So I type in 2 meters here. Next, and this is the field coordination specification. So default coordination means for this first file, 1.dat, channel number 1 is located at x equals 0, and channel number 2 is x equals 1. And then sharp point is located at x equals -8. So this is the surface coordination, which you can change arbitrarily, but it has to be consistent in terms of receiver spacing and also your sharp point distance. So I will take the default coordination provided by the program, and you move to next. And this is a text summary of all those parameters, and move next. And then you click run, and then it will save output file. So output file is saved as one file. So original 12 info files are now combined into one file, in which each individual file is now designated as record number. So original 1.dat is now designated as record number 1, and the original 2.dat is designated as a record number 2, and so on. And this chart shows the correct field geometry that I and then move to the next step, which is dispersion image generation. And there are many options that you can play with, but almost always it is sufficient to take all those default parameters and just click run dispersion image. So it is now generating 12 dispersion images, from which I will have to extract these 12 dispersion curves. So now it is moving to next step. So this is the first dispersion image. And what you do is click bounds, and then click several points along the most energetic energy trend. You see the yellow, red, black. Those are the most the highest amplitude energy. So I designate this energy trend as the fundamental mode dispersion, and then I placed several bound points. As you can see here, then the program creates upper and lower bound curves. So what I told the program to do is try to examine all the amplitudes within these upper and lower bound curves to pick the proper dispersion curve. Okay. And I stop here because the energy now becomes very weak after this. And I stopped here because the energy also becomes weak. And also the trend becomes almost a vertical trend. When the energy becomes a vertical trend, then it means it is computational artifact. Okay. So, and then I click extract. Then the program extracted this dispersion curve, and it looks very good, and save it. So first time it will ask me output file name, and then it moved to next location. And you can see here it changed slightly, which means subsurface velocity changed slightly. So I update these bound curves and then extract again and then save. So from now on, I will move a little bit faster. Extract, save, extract, save, extract. So I now may delete this, or I can include them like this. It will not make much difference, but whenever I see there is a break in energy, I would rather not include. Okay, save, extract, save, extract. So I may include a few more points here by clicking, save, extract. So I'm going to delete this also, save, and I add a few more points here. Delete this, save, extract, save, and now it changed a lot. So I'm gonna update those two bound curves like this. Extract. Probably I may want to add more bound points here. Save, and it changed also a lot. Extract, save. So I extracted all 12 dispersion curves, and now the program will move to the next step of inversion. So even within the inversion, there are many options that you can play with, but usually it is enough to accept the although the default parameters provided by the program, and all you need to do is just click run. So it displays this maximum depth of analysis, which is determined by the program based upon the field geometry that you used during data acquisition. So this depth is the most reliable depth of analysis. So I accept it. Now the program is going through numerical number crunching to find individual 1D shear wave velocity profile for each measured dispersion curve. 12 dispersion curves are passed into this inversion process. So they will, the inversion process will come up with the 12 1D shear wave velocity profiles at the end, and then create the 2D velocity cross section from all of them. So we can see here the match is very good, like almost 90%. So this is the final output. So horizontal axis represent the surface distance, and the vertical axis represent the depth. And here blue color is almost 200 or 250 meters per second. So this is a kind of steep soil. And the greenish color is about 400 or 500 meters per second, which is somewhere between soil, a weathered zone, and the rock. And this yellow color is about 700 meters per second, which is rock. So this is bedrock, and this is kind of a weathered zone, and the bedrock depth changes slightly. Here it is about 7 or 8 meters, and here is about 5 meters. So this is the demonstration of 2D cross-section generation. And now let me start demonstrating how to create 1D shear wave velocity profile, which is also known as the VS30 evaluation. So for that, you go to process here, 1D shear wave velocity profile from seismic field data in SEG2 format. So I go here, and the 6 files were collected. And let me show you the actual field. So this is the way they collected 6 field files. As you can see here, receive array remained at the same location all the time, but only sharp point changed. The reason why you would collect, well, in theory, to come up with the 1D shear wave velocity profile, all you need is one field file. But the reason why I would recommend collecting multiple files, like 6 files, by using different shot distance, is you can minimize potential adverse effect, like near field effects and far field effect, and also potential harmful ambient noise.
Sir, you are muted. Sir, you are on mute. You are on mute. Please unmute yourself. We are not able to hear you.
Unmute your side, sir.
Choon, please unmute.
Do you hear me?
Yes, now.
Okay.
Yes, sir.
I don't know why it happened. But anyway, so now I'm importing. Before that, I was showing this one. So they collected the 6 field files with the fixed receiver array, but they use the different shutter offsets. Okay, so I'm importing all those 6 field files. And now program detected that field file has a field geometry encoded. So would you like to view this? Yes. So it shows the correct field geometry. So I don't have to go through that source receiver setup process again. So I save it as a one combined field file. Okay, and it is saved as one file. And then it will move to the next step, which is the dispersion image generation. So run dispersion image. Now it is generating 6 dispersion images. Remember, all we need is one dispersion image to create one 1D shear wave velocity profile. So it now moves to the next step. So program detected that there are multiple number of dispersion images in the info file. So would you like to stack them? Yes. So the stacked one is saved. Now this is the one stacked dispersion image. So let me zoom. And then I'm gonna extract dispersion curve from this one. So I will start somewhere over here because whenever it is a flat and horizontal, it doesn't matter. You include more data points. So I stop here. I don't go further into lower frequencies because below here, you can see it becomes almost vertical, okay? And then extract and then save. So it saves the one measure the dispersion curve, and then it moves to the next step, which is inversion, and click run. So it also displays the maximum analysis depth is 85 feet. So now it displays 1D shear wave velocity profile. So this is the analyze the shear wave velocity profile, automatically analyze the shear wave velocity profile, and it shows the top, the overburden has about 250 meters per second, the shear wave velocity. In terms of feet per second, it is about 700 feet per second. And then there is abrupt increase of shear wave velocity, which is almost the 700 or 600 meters per second, which can be regarded as a bedrock. So the bedrock depth here is above 40 or 45 feet. Okay, so this is automatic result of your inversion, but this looks like a little bit unrealistic. So I'm gonna go for the next round of manual inversion by changing velocity manually like this. Okay, and you see whenever this red color occurs, it means the new fitting dispersion curve match is lower than original. Original one, as you can see here on top, is 89.15. Now the new one is 88.8, which is lower. So, but I can continue doing this and see if now the blue color means it is a better fitting. So, okay, like this. So this is 88. Okay, so I can go for another inversion like this. Now it gives me a higher number, 89.225. So I would rather take this one as my final velocity profile. Although the first automatic result is good enough, but I would prefer having this one. So I will save this one as my final output. And then if you want to come up with a seismic site characterization or seismic site class, then you click this VS 30 meter button on the right corner here. And then it provides two options, USA, any HRP standard or Eurocode. So I will choose, you can choose either one. So I will choose the USA. And then it shows me this seismic class C and the VS30. In this case, it becomes a VS 100 feet because they use the feet distance unit. So the value is 1236 feet per second. So now the program asked me, would you like to display seismic site characterization table? Yes. Now it is displaying this seismic site characterization table. So the value was 1236, so which is somewhere over here. So seismic site class C here. Okay, and this is the end of the my ParkSEIS software demonstration, and also the end of my presentation today. Any questions?
Thank you, Dr. Park. Now we've got quite a few questions which are in your chat box. If you see on the top column, there's a chat. If you just press that, you will find a number of people have issued their questions. So if you could just go through that and answer each one as you can.
Where should I go? On the top right corner?
No, it's in the center. It's called chat, C-H-A-T, chat. Just press that and you should get all the questions that everybody has written in.
Okay, now it is.
I request everybody, please mute yourself. Yeah, I muted all of them. I request you don't unmute yourself. If you have any questions, please raise your hand.
Okay, do you hear me?
Yeah.
Okay, so. So first one, which type of geophone is good for the MASW technique? It should be a vertical geophone. And as I said earlier, we are dealing with the Rayleigh type of surface waves, although we can deal with the lobe waves. So to deal with the Rayleigh type of surface waves, you have to use a vertical geophone. To deal with the lobe waves, you have to use a horizontal geophone. But the reason why I don't usually recommend measuring lobe waves is measuring or generation and recording lobe waves is a lot more difficult than Rayleigh wave. It is because of the gravitational forces always acting vertically. So it is it is easier to make a vertical impact, and also it is easier to record the vertical vibration. Okay, and now move to the second question. Horizontal or vertical, so for 4.5 hertz. We allow you to ask you a question. Okay. If we have acquired data for MASW using 4.5 hertz phone, can we pick a dispersion curve below 4.5 hertz? Yes, you can. So as I said during my presentation, even with the 4.5 hertz phone, it is not sharp cut. Below 4.5 hertz, the geophone's response curve gradually decreases. So actually you can record all the way down to 1 hertz by using 4.5 hertz phone. Again, surface waves are very strong. So you don't have to worry about that attenuation effect by the geophone too much. And first, according to you, what is the confidence in imaging shallow, which is shallower than 10-meter structures using MASW? I understand that we need a lot of high frequencies for this to happen, but high frequencies are typically noisy and contaminated by the presence of higher order modes. What are the primary? So answering number one, to deal with the shallow depths, here you indicated depth shallow than 10 meter is shallow, but it is indeed the most common depth range nowadays dealt with the MASW. So for 10-meter depth coverage, your surface waves, signal surface waves, will have to be in the frequency range somewhere between 10 hertz and about 50 hertz. Okay, so 50 hertz is not that much high to be contaminated by the high frequency side, but even as high as 100 hertz, you will see very strong surface waves. So it's not, I mean, the surface waves up to 100 hertz, they are not much vulnerable and not often contaminated by any ambient noise. And higher modes will tend to dominate more as you go to higher frequencies, but you will almost always be able to distinguish higher modes from, or a fundamental mode from higher modes. And number two, what are the primary coherent noises that result in a lot of bias in the BS estimate? Coherent noise, well, you know, if there are any coherent noise, like a traffic, they will contribute to your dispersion curve creation. Of course, there will be traffic vibration coming into your array from sideways in slant ways, but those surface waves will be very much filtered out during your wave field transformation, because your wave field transformation focuses into only inline propagation surface waves. So even if your traffic vibrations are coming from all azimuths or from all angles, the wave field transformation will focus into only those surface waves arrived along the inline propagation. So you don't have to worry about too much. And so I would not say there is not specific coherent noise that can be detrimental to your analysis. And number three, can you comment on the applicability of full waveform inversion algorithms to this setting? Yes, this is a very good question. So full waveform inversion is based upon using your raw data, seismic waveform as a signal. You don't go through any the subsequent dispersion analysis or inversion analysis. You just use your measure the full waveform of this, the seismic waves, and then you go through so-called the full elastic wave for the modeling algorithm, which is used for your inversion algorithm as well. So that one is very much powerful in theory, but in reality, there are many complications coming into play. For example, your waveform may change a lot depending on your equipment, and also your waveform may change a lot depending on other properties of subsurface, like attenuation properties, which is completely independent of your seismic velocities. And also your ambient noise will play a very critical role to become detrimental to your analysis as well. So my answer is full waveform inversion is it seems the way to go, but at this moment it is still remains at the research level, and I hope it will go through all hurdles and become practical in the near future. And then next question is, what is the role of source offset and movement step for successful source. Okay, so source offset is important. In other words, if your shot point is too close to your receiver array, then for several geophones very close to your shot point will not have surface waves recorded, because for the surface wave generation you need a certain distance away. Otherwise, the surface waves are not generated, and you near offset geophones will not contain useful signal. So that shot offset. So how much is the optimum shot offset? Which is usually, rule of thumb is, which is about 25% of your receiver array. So if you use 24 channel receiver array, then I usually take the 6 times of your receiver spacing to become that shot offset distance. And then the next question was the movement step, which is the interval, survey interval. How much you can move after you collect the one file? How much can you move everything to next location? Usually it is a 1 receiver spacing. So if you use a 1 meter receiver spacing, you move everything by 1 meter for next measurement, which will give you the highest lateral resolution. But if you expect there is not much horizontal variation, then you can increase that interval to multiple number of your receiver spacings. So sometimes if I see there is not much bedrock variation or not much stiffness variation within the soil, then I usually move by multiple, like 3 receiver spacings or sometimes 4 receiver spacings like that. So it will make you be able to move much faster to cover long distance. Okay, so and then is it possible to automate the picking of dispersion curve, or is it always necessary to verify while picking? Yeah, this is a very good question also. So today I did not have any chance to demonstrate automatic function of the ParkSEIS. Well, why don't I demonstrate? It is very quick. So let me go to auto here, and then to the velocity cross section from. I already have this source receiver encoded data here. So let me choose this one, and then click automatic processor. So now the program goes through full automatic processor, in which the program will generate dispersion image, and then it will pick dispersion curve on behalf of me. So let's compare this result against the manual results that I came up with during my demonstration. So this will take only probably one minute.
We can't see your screen.
Oh, I'm sorry. All right, so here, where should I go? Here. Do you see my screen now?
Not yet, Choon. Can you please try again?
Now do you see?
Yes, yes, we are seeing your screen.
Yes.
Okay, now let me show it again. So I go to auto here, and then I selected the file that I already encoded the field geometry. Okay, and then this is the automatic processing. So I was demonstrating this one. So this is a full automatic processing with the ParkSEIS, and it will generate its own velocity cross section, which I will compare against my manual processing result. So automatic picking algorithm is not perfect, but I would say it is good enough. And as I tested with the many different field data set, its performance was almost 90% in comparison to the results that I manually obtained. So for the most of the beginners, I believe this automatic approach will be good enough, and it will be very much useful for learning purposes as well. So this is my, the automatic result, and let me compare this one against the manual result, which is here. Which is this one. So I'm gonna put, so plus this, okay, so this is automatic result, and this is my manual result. So there is a little bit difference here, but in terms of general trend of bedrock here, it's quite similar, and the overburden velocities are quite similar as well. So again, this one is the automatic result, and this one is my manual result. So if I pick the my manual result more carefully, probably the results may look closer to this automatic results. So anyway, let me go back to the original question. So it is possible to pick the dispersion curves automatically. And let me stop this sharing and then go to chat again. So where was I? Okay. So the next question is, what is meant by fundamental model? How can we identify it in the dispersion image? This is hello? Can you hear me?
Yes, we can hear you.
Okay. So the next question is, what is meant by fundamental model? How can we identify it in the dispersion image? This is a very good question also. So, well, whenever you make a vibration, then there are always multiple modes generated. It is a nature. So you multiple modes of propagation, but what we use is a fundamental mode. And in theory, according to the theory, fundamental mode almost always takes the strongest energy. So in other words, whenever you observed in your dispersion image with the strongest energy, then it is almost always the fundamental mode. And also, fundamental mode always occurs at the low frequency range with the lowest phase velocity range. So if you see multiple coherent dispersion trends occurring in the dispersion image with almost the same energy level, then you can choose the one that occurs at the lower frequency range with the lower phase velocity. Next one is why is the amplitude higher amplitude signal at lower frequency range is generally not picked? Because, well, this is also a good question, because very often very high amplitude energy occurring at the very low frequency end side of your dispersion image, they are almost always computational artifacts. So computational artifacts, as I said earlier, are inevitable. So depending upon your program software, some software completely mute out that computational artifact part, and some program leaves them there for you to actually judge, because sometimes it is very tricky to distinguish that computational artifact from your useful energy part of the fundamental mode. So next question is, while applying any source / body waves are also generated, how does the software deal with the contamination of surface waves by the body wave generated by the. This is another good question. So body waves first will always occur much higher frequency than surface waves. So for example, if surface wave fundamental mode occurs somewhere between 10 and 50 hertz, body wave usually occurs at twice or sometimes 3 times higher frequency range, like 100 or 150 hertz or higher frequency. So that is a very good way of distinguishing body wave and from your surface waves. And also body waves usually will occur with a much higher velocities. So that is a second criterion that you can use. The next one is why the higher amplitude signal, the low frequency. Okay, I covered that. Without inputting the initial model, is our results stable, reliable? So without the initial model, well, you have to have an initial model of a certain kind anyway. I mean, the inversion cannot start without any initial model at all. So, but probably you might have meant initial model of arbitrary velocity model. That can be used also, but it should not be too much different because of so-called the non-uniqueness issue in inversion. So that's why a good program uses a very good algorithm to create very reasonable initial model. The next question is, can I ask my question? It's difficult to write all the technicality, okay? What is the full wave from inversion? I cover that. Okay.
Hello.
Yeah, I'm reading the comments here and the questions. Can you throw some light on the BSA and its accuracy in determining any void? So BSA stands for backscattering analysis. So this is another very good question. Backscattering analysis is very good to detect the void, but it is at the very early stage of research, which I studied. I don't know if anyone else here studied, which I studied after I left the KGS. So and the algorithm incorporated in the ParkSEIS is the as best as I could come up with in terms of algorithm about 5 years ago. So I think it still needs some empirical calibrations, but I believe this it can be very effective in comparison to other geophysical methods to detect a void. So my answer here is BSA is a very effective in terms of seismic technique to detect the subsurface anomaly like a voice. But I would recommend you doing your own research to figure out the some other parameters to, that can influence performance of that algorithm. Can we use the deep seismic sounding data for MASW? I guess the deep sounding seismic data means the like a deep reflection seismic data. For example, the oil exploration seismic data. You may be able to use it, but you have to check the geophones used during the data collection, and also if the acquisition filter was used. If, for example, during the conventional reflection seismic survey, people often use the analog local filter to cut out ground draw, which is a surface wave. So if that's the case, then the data may not have sufficient energy for surface waves. But otherwise, still, I see a lot of those legacy data sets still have a good amount of surface waves left. So again, try to use those data and see how much low frequency components each data set has. Can you use the Subsurface software instead of ParkSEIS for MASW survey? Of course, the Subsurface is the the predecessor of the ParkSEIS that I developed while I was at the working at the Kansas Geological Survey. And ParkSEIS is a kind of a second generation of SurfSEIS. Can we do backscattering analysis using ParkSEIS? Yes, ParkSEIS has the only package that has a backscattering analysis algorithm. Please share the PPT to mail. I'm not sure. We will have to talk to the HGS India. If we can increase the receiver spread, we can get deeper information. Is it maintain the resolution and is it provide better inversion curves? No, simply merely increasing your investigation depth does not give you any better inversion. So whenever you increase your investigation depth, your vertical resolution inherently decreases your depth. When we include higher modes for inversion, why higher modes are generated? Well, as I said earlier, higher modes are always generated because of that. It is nature. So the amount of energy imparted into higher modes are determined by two factors. The first, velocity structure. Second, attenuation structure. So we are dealing here is velocity structure only. And so, in other words, there are a lot more complications than people would normally imagine. And higher mode, well, there was a higher mode inversion technique came out almost 20 years ago. At that time, we thought we know the actual model identity of higher modes curves that we measure, but it turned out to be no. A lot of cases, our let's say the first higher mode dispersion curve that I measured, it turns out to be third mode higher mode, and second mode higher mode dispersion curve that I thought actually consisted of second, third, fourth combined mode like that. So higher mode occurrence is a lot more complicated than people normally assumed at the beginning of this research about 10 or 15 years ago. So, and then after that, people almost quit using so-called multimode inversion. Instead, people are trying to go into different directions, like the full waveform inversion is one direction, and another direction is a dispersion spectrum inversion, or sometimes they call it sometimes dispersion spectrum inversion, but I would call it dispersion image inversion. Is it required to pick higher mode dispersion curve for the velocity profile? No, you don't need to pick higher mode curve. Rayleigh wave is a surface wave, but how we are estimating shear wave velocity from Rayleigh wave, I already covered that during a presentation. For increasing resolution in top layer, what will be typical receiver spacing? Oh, so to increase resolution in top layer, you have to shorten your receiver staging. In other words, you should not use a too long receiver array to cover your depth. For example, if you want to cover only top 5 meter depth range, then your receiver array length should not be longer than 10 meter. In other words, if you use 5 meter receiver spacing with 24 channel, your receiver array length will be longer than 100 meter. But you are trying to cover only 5 meter top depth, then your 5 meter will be almost completely lost. It will be invisible. So the point here is that you have to use proper length of your receiver array, just like the antenna concept that I mentioned during my presentation. And without inputting the initial model, is your results stable, reliable? Well, I already covered that. Why the thickness of layers are kept constant while doing inversion? Well, this is another very good question. Inversion, as you introduce more variables, which means you are introducing more degrees of freedom, then you actually make inversion more complicated. In other words, it is riskier. You are increasing the risk of coming up with more computational artifacts in your result. So there should be optimum number of degree of freedom in your inversion algorithm. So in that sense, you have to keep your number of layers during your inversion. And the 10-layer model incorporated in the ParkSEIS is the optimum number of layers determined through a lot of empirical experience. But the ParkSEIS has its own option to make that layer thickness as another variable. But that's not default option. Now, can we get ParkSEIS software for educational purposes? That is something that I don't know. You have to ask the HGS India. What is the maximum data size, load capacity, number of shot gatherers at once of the software? Well, we tested the number of shot gatherers up to 500 or 750 shot gatherers of 24 channel, and we did not have any issue. Near field and far field effect and their removal. Well, you cannot to remove or to attenuate, to minimize the near and far field effect. The best, all you can do is you select the optimum field geometry. In other words, the optimum distance of your shot point. But this is not that much severe, so that's why the rule of thumb is about 25% of your total receiver array length to be your shot point. Top two modes are crossing each other. Black and blue, is it possible? Two modes cannot cross each other. So probably it might have been the display illusion. No two modes of dispersion curves across each other. It poses the nature of inversion. Multiple solutions exist. How can I be 95% sure that I obtained the good result? Well, that's why inversion algorithm is so important. So as I said earlier, you have to start with a very, very reasonable initial model at the beginning, and then your searching algorithm also must be very much reasonable. So inversion needs a lot of empirical calibration. So that 95% confidence that I mentioned during my presentation is based upon data analysis results. We provide the data analysis services, and we've been processing almost 2,000 different data sets during last about 15 years. Absolutely true. There can be many issues with the use of the higher harmonics. Okay. What's the minimum size of anomaly that can be detected using MASW? So yeah, this is another good question. For example, if your anomaly size, I usually take about 20% of depth. In other words, if your anomaly exists at 10-meter depth, then its diameter should be at least 2 meters or bigger. How do you handle the non-uniqueness issue in 1D inversion? So I already answered some questions, and also I demonstrated how you can actually minimize theoretical non-uniqueness risk by using your own manual adjustment of the final justice profile at the end of that automatic inversion. Is it possible to perform multi-component inversion or joint inversion in ParkSEIS? Multi-component inversion is not possible, but you can use joint inversion. Joint inversion, I guess, means joint inversion on multiple modes. It is possible on ParkSEIS if you generate multiple modes of dispersion curves on the modeled dispersion image, which you can generate by using ParkSEIS. Hello, Anil. Am I doing okay with the time? It's already past the 1.5 hours.
Yes, it's quite late. It's 8:15 in the evening here, so maybe I don't know how many other questions there are. I think this is the last question. So if you can just answer
I'm
point
reaching
3 and 4.
Yeah.
Yeah.
Okay, so I will continue then. Whether dispersion image inversion is better than modal inversion? Well, in theory, dispersion image inversion is much better than the modal inversion if it works. In other words, you have to find the optimization technique, very good optimization technique, but it is very difficult and it takes a lot of time. So for that approach to become practical, well, I don't think it is quite ready yet. What is the main drawback of dispersion image inversion? Again, the optimization technique is not that much practical yet. Is the apparent dispersion curve better for inversion? Well, it depends upon your inversion algorithm. This is a good question also. So apparent dispersion curve occurs very often. And if your inversion algorithm does not account for that apparent dispersion mode, then you may end up with a lot of erroneous result. But ParkSEIS has its own algorithm to detect the apparent dispersion trend. So the inversion actually goes simultaneously with the modal inversion and also apparent mode inversion as well. Okay, now the last question, I think. Why most of the time only fundamental mode is picked and the higher mode is ignored? I already answered that. What will be the effect in shear wave velocity profile if all modes are picked? So yeah, if you pick all modes and if you know the modal identity of your all picked dispersion curves, then you can increase resolution of your results a lot more. But again, as I said earlier, we are having unexpected complications, especially we don't know the identity of our picked higher mode dispersion curve.
I think this is it. Yeah, this is it, and I think we need to thank you, Dr. Park, for an excellent presentation. And gentlemen, ladies, if you have any questions, you can easily send them to us, or you can directly address them to Dr. Park, and I'm sure he'll be happy to answer them to you. And I thank all of you for staying so late to see this presentation. And hopefully, we should be able to answer any of your questions that may crop up during your work. Thank you very much, everybody. And good night.
Thank you very much, Anil, and
Thank you.
Thanks for participation, everybody.
Thank you.
Thank you, Dr. Choon.
Thank you, sir.